more straightforward in some ways, but longer and I suppose altogether slightly harder way. We'll pause for a second. Okay, let me show you another way of looking at this, which is perhaps more pedestrian. Let me start with probability that 3 are broken by m are greater than or equal to 3 broken by the mathematician, given 5 broken in all. In other words, I'm setting this up as a conditional probability, and that's equal to the probability that 3 are broken by the mathematician are greater than or equal to 3 broken by the mathematician, and 5 are broken in all, over the probability that 5 are broken in all. So to solve this, I need to work out the numerator and the denominator of this and divide one by the other, and that will give me the solution. So to do this, let's work on the denominator first. So for the denominator, I want to know the probability that these 4 people sharing this flat break 5, exactly 5. And to do this, it really helps if you know a little bit more about the Poisson distribution. So if we've got A, B, C, and M, who are the 4 people in the flat, A, B, C are the 3 others, M is the mathematician, they've all got a Poisson distribution where its lambda's the parameter. And the thing about Poisson distribution, what I want to know is if all 4 of them are together, what's the sum of these? And the sum of a Poisson distribution is another Poisson distribution where you simply add the parameters. So the total breakage, T, which is A plus B plus C plus M, is a Poisson distribution for lambda. It's not that hard to show that, but I'm not going to show that here. And that means the probability that the total is equal to 5 is equal to this Poisson formula exactly, but where instead of lambda, I've got 4 lambda. So I have e to the minus 4 lambda, and then lambda to the n, except it's not lambda to the n, it's 4 lambda to the n, and it's not n, of course, because I'm interested in it being 5, over 5 factorial. And that's the probability we're going to have on the denominator. We don't know what lambda is, but it'll turn out that lambda cancels. Okay. Let me just put that in, even though I don't know the numerator yet. I'll leave the numerator there. It's e to the minus 4 lambda, lambda to the 5, 4 to the power 5, over 120. 5 factorial. Okay, so now we've got to work out the numerator. What's the probability that 5 are broken in all and 3 are broken by the mathematician? So let me change color and look at it this way. And I'm giving myself a little more space here. I'm going to look here. A, B, C, and M. And I want to think of the different ways in which they can break 5 plates, where the mathematician breaks at least 3 of them. So the simplest way is that the mathematician breaks them all. And the next simplest way is that the mathematician breaks 4 of them, and perhaps it's A who breaks the other one, or perhaps it's B, or perhaps it's C. And perhaps, though, he only breaks 3 of them. That's a little bit more complicated. So perhaps it was A who broke the other 2, or perhaps it was B, or perhaps it was C. Or perhaps the mathematician broke 3, but 1 each among perhaps A and B, or perhaps A and C, and B didn't break any, or perhaps B and C. And those 10 possibilities, or all the possibilities there are, for distributing the breakage of the plates among the 4 of them, given that the mathematician has to break at least 3. And this slightly more laborious way of working this out simply works out the probability of this happening. And the probability that A breaks 0 plates is e to the minus lambda. That's what a Poisson distribution means for breaking 0. And the probability B breaks 0 is e to the minus lambda. And the probability C breaks 0 is e to the minus lambda. And the probability that M breaks 5 is lambda to the 5 over 5 factorial e to the minus lambda. And let me just simplify that a little bit. Put that equal to e to the minus lambda times e to the minus lambda times e to the minus lambda times e to the minus lambda is e to the minus 4 lambda. And what I'm left with is lambda to the 5, that factors there. And now what I'm left with is 1 over 5 factorial, which I'll just put in as 1 over 120. Okay, so let me work out the next one. So this one is the probability that A breaks 1 plate, and B breaks 0, and C breaks 0, and M breaks 4. So the probability that A breaks 1 plate is lambda e to the minus lambda. The probability that B breaks 0 is e to the minus lambda. And the probability C, e to the minus lambda. And the probability that M breaks 4 is lambda to the power 4 over 4 factorial, e to the minus lambda. And if we simplify that a little bit, we find that that is e to the minus lambda, e to the minus lambda, e to the minus lambda. It's e to the minus 4 lambda. You also see that there's a lambda here and a lambda to the power 4 there, so there's also a power of lambda to the 5. And now what number is there along with that? It's 1 over 4 factorial, which is 1 over 24. Now, things get a little easier because the probability of the next one is the same, because the probability that A breaks 1 and B0 and C0 and M4 is the same as A0 and B1 and C0 and M4. It's the same, and this one's the same as well. So to continue a little bit, we've got here the probability that A breaks 2, which is lambda squared over 2 factorial e to the minus lambda, that B breaks 0, which is e to the minus lambda, and C0 e to the minus lambda, and M3, which is lambda to the power 3 over 3 factorial e to the minus lambda, and that is equal to e to the minus 4 lambda again, because we've got e to the minus lambda, 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 4 of them, so that's e to the minus 4 lambda, lambda to the 5, and then there's a fraction here, which is 1 over 2 factorial times 3 factorial, which is 1 over, well, 2 times 6, which is 12. And the 2003 possibility is the same probability as the 0203 probability, and the 0023 probability. So I've actually just got one more to work out. So this is a 1103. So let me, quick as I can, e to the minus lambda, e to the minus lambda, e to the minus lambda, that's c, and then it's lambda 3 over 3 factorial, e to the minus lambda, and if you multiply those together, it's e to the minus 4 lambda, lambda to the 5, as it is in every term. And what's the fraction here? It's 1 over 3 factorial, which is 1 over 6. And these two combinations are the same. And these are all mutually exclusive, so I need to add them up. And so this in the end turns out into a little bit of addition of fractions. So let me just go down here and I'll turn into a fraction having colour. And what I want to add up is 1 over 120 plus 1 over 24, except it's 3 over 24, because I have 3 of those possibilities here. Here are the 3 possibilities. And now I've got 3 over 12 and then 3 over 6. 3 over 12 plus 3 over 6. I want to see how many over 120 that is. 1 plus 15 plus 30 plus 60, which is equal to 106 over 120. Okay, so that's 106 over 120 times e to the minus 4 lambda, lambda to the 5. Okay, so let me go back up here and put in the probability that greater than or equal to 3 are broken by m and 5 broken in all is that probability that we've just worked out there, which is 106 over 120 times e to the minus 4 lambda, lambda to the 5. Now I think I should take some red pen to do some cancelling, because that's what we want to do. Happily, the e to the minus 4 lambda cancels and the lambda to the 5 cancels, and what's more, the 120, or we can multiply top and bottom by 120, and that cancels, and that gives us 106 on the top over 4 to the power 5, which is equal to 106 over 1024, which is what we had before, and as we had before, it's 0.1035. That again is the answer, having worked with the Poisson distribution. As it sort of leads you towards, by talking about the Poisson distribution here, suggests maybe you should go by that, but that's definitely a much longer way of doing it, not particularly recommended, but you can do it. That's all for now.